Let's do another Gauss's law problem. So here we have a coaxial cable. You can at least see the top part of it here in the picture, with a metal wire that's running down the center that has a charge per unit length of plus lambda. Air surrounds the wire, which is a little bit weird, but anyway. And on the outside, we have a metal cylindrical shell that has an inner radius of R1 and an outer radius of R2. And the outer cylindrical shell has a net charge per unit length of negative lambda. And so what we want to do is we want to determine the electric field for these various distances between the wire and where the cylindrical shell starts, inside the cylindrical shell, and then on the outside of the whole thing. Let's use Gauss's law. For R less than R1, the charge that's enclosed, Gauss's law, same thing as always, the surface integral of E dot dA. I leave a little space between the E and the dA because it helps showing my work later. Now, what is the charge that is enclosed? So what we need here is we need a Gaussian cylinder that has a radius R that is less than R1. So there it is right there. I could draw it bigger or shorter, but it doesn't matter. And that's got a certain height or length. Let's call it L this time. Let me scoot that up so you can see that. This is on the outside of the wire, but within the cylindrical shell. So what's the charge that is inside this thing? Well, it's equal to lambda times the length. So this numerator is going to turn into lambda times L. At any point on the lateral surface of this Gaussian surface, the electric field has a uniform magnitude, so I can make the integral move to right over there. And when we integrate dA, we just get A. So what is the surface area that is getting pierced by these electric field lines that are going out like spokes on a wheel from this wire that's running down the center? And that's going to be the lateral surface area of this cylinder, which is equal to 2 pi times little r times the height. We don't include the top or the bottom of this Gaussian cylinder because the top and the bottom are not pierced by field lines. The field lines scrape them as they are spoking out, but they don't pierce the top or the bottom. When we simplify this, what does this give us? The L's will cancel, so it doesn't matter what height of a Gaussian cylinder we chose. And that looks to me like E is going to be equal to lambda over 2 pi epsilon naught r. So the electric field is getting weaker as we get away from this central wire. All right, well, what about for when we are within the metal cylinder? Well, if this is in electrostatic equilibrium, anytime you're in the interior of a metal that's in electrostatic equilibrium, the electric field is equal to 0, always. So that was an easy one. What about when R is greater than R2? So now our Gaussian cylinder is going to be, let's say, out here. I'm just going to draw them real short because we said it doesn't really matter how tall you draw the cylinder. If you want to give it a dimension, we could call it h. So what's Gauss's law? It's the charge that's enclosed divided by epsilon naught equal to the surface integral of E dot dA. Now, what's the charge that's enclosed? Well, here's the neat thing. We just did a problem in the previous video. If you haven't seen it, you might want to take a look at it, where the charge that's going to be on the interior surface is exactly equal and opposite to the charge that's on the thing in the middle. So the charge on the thing in the middle is plus lambda, which means the interior surface of this metal cylinder has all of the negative lambda, which means what? What's the net charge that's enclosed by this little squatty cylinder? 0. And if the net charge that's enclosed is 0, that by definition requires that the electric field also be 0. So if we're going to graph this, we're going to make a graph that looks kind of like this. We're going to say on the horizontal axis, there's R. Here's R1 right there, and there's R2. And according to what we have here, as we go from the center of this thing, which is where the wire is, the electric field, it's going to slope down like that. I'll put a little equation there. E is proportional to 1 over R. That's what this equation here that's boxed in at the top says. All that other stuff is a constant. Lambda is a constant, epsilon naught, pi, they're all constants. The electric field is proportional to 1 over R. And then when we get to that metal cylinder, the electric field equals 0. And then as we go further away from it, the electric field equals 0. The electric field equals 0 there, and it equals 0 there.